Okay, yeah, so as Justin said, today we're going to talk about testing smart contracts. I'm curious, how many of you have written smart contracts or are thinking about writing smart contracts? Okay, cool, so this is very relevant, awesome. Um, okay, so my name is Jake Urban. Here are my usernames on all the platforms that you can find me at. You'll notice that that is not my face. And that's because I'm filling in for Lee, who you may recognize, that he used the same profile picture on Discord. And he originally wrote all this content, so shout out to Lee for being awesome, and also I want to set your expectations accordingly. So here we go, let's talk about testing. So how do we know that something works, right? So scientists, forever have used the scientific method, and Wikipedia describes the scientific method, as a method for acquiring knowledge that involves careful observation coupled with rigorous skepticism. And I feel like everybody kind of understands that observation is kind of the key point for the scientific method, right? But rigorous skepticism, that may not have been a term you've heard about. So what does that really mean? Wikipedia goes on to say that rigorous skepticism is necessary because cognitive assumptions can distort the interpretation of observation. So if we're not being rigorously skeptical of what we're seeing, then we don't really know something works, right? I mean, how many of you have run your program or what you're building, you've tested the happy path, it works, and you're like, done, right? Like, let's move on, and then later learn to find out that's not true. So rigorous skepticism is super important, and really rigorous skepticism is about the elimination of assumptions. Assumptions make us look dumb. We've all been there before. We've all made assumptions and proceeded on and later learned that we have bugs. Dijkstra said about bugs that if debugging is the process of removing software bugs, then programming must be the process of actually putting them in. And he's highlighting, obviously, that as we program, it's unavoidable. We're going to be creating bugs. As much as we're creating stuff that makes our lives easier, we're also making stuff that's going to make at least the developer's life harder. So testing needs to be, done iteratively as you develop, right? Not at the end. It should be done as you're writing your code, because as you're writing your code, you're creating bugs that need to be tested and fixed. And obviously, the longer we do what we do, the longer you've been a software engineer, the longer you've written software, you're going to get better at avoiding writing bugs, right? You're going to be able to notice when you're making assumptions and course correct. But you're not always going to do that. Nobody's going to be perfect. It's unavoidable no matter, even if you're Lee, you're going to be writing bugs. So, what do we do, right? Like, given that we're always creating bugs, the obvious thing is that we test. And so what are good tests, right? Good tests, first and foremost, give us confidence that the software is doing what we expect it to be doing. But it also gives us confidence to change the code, right? So like, if it's working at a certain point in time, we change the code. If you don't have tests, all bets are off, right? And you have to retest. So having a good set of tests tells you if something is different about the changes that you make that you didn't expect. And then it also helps us understand how much of what you're building changed, right? If you want to make a change that is limited in scope, right? You change something in the code that you think is fairly isolated, but then it ends up having all these cascading effects. You're not going to know that, because if you make an assumption about what that code does and you test what that specific feature that's relevant to what you think the code does, and it has other impacts, you're not going to know that, right? So testing tells you not just, hey, this changed what you expected it to change, but it also changed all this other stuff, right, that you have to be aware of. So I guess what I'm saying is testing, good tests at least, don't make assumptions, right? Like, we can make assumptions ourselves, but our tests shouldn't. And so a common theme when we were building smart contracts on Stellar is that we wanted testing to be kind of a first-class citizen, in the same way that actually writing your smart contracts were. So we wanted to bring all the advantages of Stellar prior to smart contracts into the smart contract world. I think, I don't know how many of you were building on Stellar prior to smart contracts, but it was fairly straightforward, because Stellar had this limited set of operations that were very well defined. Because all the operations and all the things you could do on Stellar were well defined, we had all this tooling that allowed you to utilize those operations and understand the effects things like Stellar Lab, which Jane is working on. And we wanted you to have that same experience when we're building smart contracts, even though what you could do on Stellar became so much more complex. So what does that look like? What does testing as a first-class concern look like on Stellar? Well, first and foremost, we wanted your entire testing or contract development lifecycle to be in one language, which is Rust. If you're coming from the EVM world, you'll know that this is particularly valuable because people in the EVM world did not have this capability for the first handful of years that the EVM was around. You had to write Solidity contracts, and then your tests were in JavaScript if you were using something like Hardhat. That's changed now. They've kind of wised up and they created Foundry, which allows you to write Solidity tests. But that was not the case for quite a while, and we definitely didn't want to have our ecosystem wait around for writing contracts or tests in Rust. And obviously, it allows, if you have one language, to reduce context switching, right? So what that really means is that if you know how to write smart contracts, then you know how to test those smart contracts. You can use the same types that you've defined in your contract to write your tests. You know how to write Rust, so you know how to write those tests. There's a lot of value not having to go from Rust to JavaScript or some other language or some other programming paradigm or environment. We also wanted developers to be able to test their contracts in an environment as close as possible to mainnet. And a lot of the points that I'm going to go over later in this talk really focus on this point in particular. We don't want you to have the classic problem of things working locally or working on your machine but not others. So that was a big focus when we developed smart contracts. And on top of that, we have all these advanced approaches, which we'll go into a little bit as well, things like property testing and fuzzing. So Stellar's smart contracts platform is great, and it's really something. One of the core tenets of it was for it to be safe and secure. So testing is that kind of first-class principle, as I mentioned earlier. All these efforts were made, to make sure that things were going to be safe when you're writing contracts. So what do I mean when I say testing, right? Because I think all of us kind of have this idea of what testing is. Testing's a lot. All right, there's unit tests, but there's also mocks, test snapshots, end-to-end tests, fuzzing, invariant testing, differential testing, formal verification. There's a lot that you can do to test your code. We're going to touch on actually a good chunk of these as well, but there's also going to be stuff that we're not going to talk about. And to be as practical as possible, we're going to look at the code. So from now on, there's been a lot of slides with nice graphics and stuff. We're going to dig into the code a little bit, actually show you what it looks like to actually use a lot of these capabilities. If you and the kind of the point that I want to hit home here is that you have no reason to not use a lot of these features because hopefully it's going to be very easy to utilize them. So next time you're writing your smart contract and you write some unit tests, I want you to think back to this talk and recognize that there's more you can do, and it's actually pretty easy to do that. So before I dig into the code, just a quick shout out to our developers documentation. It has a lot of the information I'm going to kind of share here. It's pretty easy to get your environment spun up and start writing contracts, and you can do that on the homepage of our DevBox. Okay, so in order to show examples about testing code, we need to have something to test. This is a token contract. And it has a fairly small interface. It's actually a subset of our SEP41 token standard. It has a constructor, and constructors are actually coming in Protocol 22. So if you try to deploy this right now, it won't work. But they are coming in Protocol 22, and this also has three functions: mint, balance, and transfer. Minting obviously is to issue some amount of the asset or the token to this address. Balance is to check the balance of that address, and then transferring is obviously transferring the token from one address to another of a given amount. And then importantly here at the bottom we have kind of the description of the types of errors that you can expect to get when you call the functions on this contract. Okay. This is a test, and it's a very simple one. It expects that an address doesn't hold the token, it expects that an address that doesn't hold the token will have a balance of 0. So let's step through how this works. First, it's going to spin up a Soroban environment. This is called the env, or the env value. It's then going to generate the admin address and then register the token contract So you'll see that we're passing the token contract that I defined in the prior slide, and we're also passing the admin to its constructor. Then we're generating a token client, and if you remember all the code from the prior slide, this actually wasn't there. If you go back, let's see if we can go back real quick. That contract impl or contract implementation macro at the top of the implementation block, that actually automatically auto-generates a client for your contract, which is super, super useful. So you always have a struct called your contract client available in your tests, which is very, very handy. And then finally, getting down to the bottom here, we generate an address that we want to check the balance of and assert that the balance is 0, given that we haven't minted anything to the address. If this fails, it'll print something nice to your console that lets you know that the assertion was not true. So before I move on to kind of the more advanced techniques, I do want to point out that this is really this has everything that you need at a fundamental level. The Soroban environment that you're spinning up, it's not something that you're instantiating, for all your tests. You're not registering every contract that you're testing in your test suite to the same environment, right? And then commingling state between your tests. This is completely isolated, like a proper unit test should be, and it's really lightweight to do. So you can spin up, hundreds, thousands of Soroban environments in your tests, run them in parallel, and it all executes pretty quick. And then finally, the other point I want to make is that the environment you're spinning up isn't like a testing version of the Soroban environment. This is the actual Soroban environment that's running on mainnet, which is really cool. So you can have confidence that when you're writing these tests, it's going to behave, the same way on mainnet as it will in your test, because you're literally using the same runtime or the same environment as you are on mainnet. There are some differences. There's test utilities enabled in the environment. It's using a different storage backend. I don't know if you guys are familiar with BucketListDB, but it's not using BucketListDB. There's a couple variations, but it's not a separate implementation. It's like the actual environment, and it's just got some configuration that's different. Okay. Another thing not pictured here is that this is pure Rust, right? So you can use other Rust libraries if you'd like. There's other testing libraries like Mockall or the Predicates library. And because it's Rust, you can also step through in your debugger, right? So this is not like Stellar's IDE. This is not like a specific IDE made by some business in the ecosystem. If you run VS Code or some other Rust IDE, you can debug your Rust contracts right there, which is really nice. Okay, coming back to this test, it's fairly simple. Let's turn it up a notch and do something different. This is a test that transfers one balance to the next, and it transfers from A to B. The A has a starting balance of 10, B has a balance of 0. After the transfer occurs, we are validating that the token balances have been properly updated. And one thing I want to show you is that there's a lot of code here, and I'm going to continue the test implementation in the next slide. We really need, or you guys should all, test your assertions on authorizations and events, right? So most of your contracts are probably requiring authorization from the addresses in which that your contract operates on. And your contract is probably also admitting events. You want to test that your contract is actually doing that. So here's what that looks like. You notice at the top here, we are calling the transfer function. We are mocking all of the auths. And then when we do that, we can call the auths method on the environment and assert that the authorizations required look a certain way. And in this case, we're testing that an authorization was required from A, and then that the authorization specifically was to authorize the call to transfer with those parameters there. And then finally at the bottom, we're asserting that the tokens change. So there's more to do than just testing the return value of your contract. There's more to do than just testing the state change of your contract. You also want to test the side effects as well. And this is also similar code for validating that an event that you would expect to be emitted was also emitted. So you can assert that your contract emitted an event according to a given schema. Making this a little bit more complicated, let's add a dependency. Okay, so the prior test had no dependency. You weren't calling any other contracts. In this one, we're going to add another contract. We're going to add a pause contract. So this is identified by another address that's passed in, when you're deploying the token contract. And when the when the pause contract, is paused, you shouldn't get any. You should get an error when you call any of these functions. In fact, you should get that paused error there at the bottom that we added. So when you have a dependency, it's very common for you to want to mock that dependency in your unit test. So here's what that looks like. You can define a pause struct and an implementation of the paused function that your token contract presumably calls when mint, transfer, or balance is called, maybe not balance. But this is what mocking that looks like, and you can see that we're returning false here. So when we look at the test, you'll notice that it looks more or less the same. The difference is that we're registering an additional contract here, and then we are going to call the transfer function. And we're going to assert that the balances have changed because our mocked pause contract returns false. So these calls should succeed. And then also, you want to assert your events and authorizations, as I talked about earlier. On the second test, we're going to mock the pause contract and return true. And this is what the associated test should look like, right? So instead of asserting that we get all the valid state changes that we expect, we're asserting that we're actually going to get an error in response. In fact, the paused error specifically. So this is what that looks like as well. So we've tested the obvious cases, right? The true and false case. What happens if the pause contract doesn't return true or false? Right? Like what would happen to your implementation? How do you figure that out? This is an assumption. We're assuming that the pause contract returns true or false. We don't actually know if that's the case, but we're implementing it as such in our tests, and that's all that we can verify based on the tests that we have right now. So this is to point out that mocking has limitations, right? Actually, mocking is the explicit action of making an assumption. And so mocking has its use, but we want to be conscientious and intentional about, when we mock and recognize that, we're making an assumption there, we may want to test that assumption a different way. So you may have heard this story before. A software tester walks into a bar and he orders 1 drink, 2 drinks, 0 drinks, 99,999,000, lots of drinks, a lizard in a glass, -1 drinks, a string drinks, and then calls it a day and says, okay, I ran my test, seems like it works, right? Then a real customer walks into your bar and asks where the bathroom is, and the bar blows up. This is the point that I want to make, which is that unit testing is not enough. Unit testing is often the first thing that we do. It actually is incredibly valuable, but maybe it gets us 80% there, and that remaining 20% is still significant. Actually, in most cases, I don't know, unless you're very good testers, you probably are not getting 80% there with your unit tests. So what more can we do? We're going to talk about these approaches here. So there's going to be quite a bit that we're covering. And all of them are extremely useful, and I'm excited to kind of dig into it because, as I said earlier, like this was not my talk, and so I definitely learned a lot when I was walking through these myself, and I'm sure you will too. Okay, so let's test with real dependencies, right? So in our prior example, we're mocking this pause contract, right? How can we avoid that? You can actually fetch the contract that you're dependent on from the network and write it to your local file system. So you'll see here we're using the Stellar CLI that Chad kind of dove into in his talk. We're providing the contract that we want to download, and we're writing the actual WASM that's executed on-chain to your local file system at pause.wasm. And once you have that WASM file, you can import it into your test. So we have that contract import macro. You specify the file path, and it loads it into a Rust module. And then you register that module with your environment or your Soroban environment, just like if you were to register a contract that was defined in your file or in your project. there's almost no difference syntactically between doing those two things. So this is how you actually test a real dependency. When you execute or call the functions that the contract offers after registering a downloaded contract, you're executing the same exact code that's going to be running on mainnet, which is pretty awesome. The rest of the test is identical. There's nothing you need to change because of the fact that you're using a downloaded contract. Everything is the same. So you just have to fetch the contract from the network, you register it, and then you can test it. You load it and then you test it or register it. So super simple. Highly recommend that you do this. And I also want to point out that even if you're building to an interface, let's say you're building an AMM or a liquidity pool, and your contract is dealing with Stellar assets a lot. Stellar assets all mostly comply with the Stellar asset contract or the SEP41 interface. So when you download a contract that implements that interface, you may be getting different behavior depending on what that token is. You're still testing the interface, which is nice. And it's better than mocking, I guess is what I'll say. You're going to get a higher level of confidence by downloading a handful of the tokens that your contract interacts with. So you're going to get a better feel for whether or not your implementation actually works as expected if you actually download and actually register contracts that execute on mainnet. So the next strategy is testing with real data. So I want to point out that when you downloaded that contract earlier, you downloaded the implementation, but you're not downloading the state that the contract manages. So when you register a downloaded contract in your environment, you kind of like redeploying. It has like the empty or default state that your contract would have when you originally deployed it to mainnet. So how do we, and this is bad, right? Because like you may want to like assume naturally that when you call this contract, it's going to have some state in it, right? Or it may have state that's modified. So using a different command, you can use the Stellar snapshot subcommand to create a snapshot of a contract at a given point in time. And so this is not just downloading the code or the implementation that runs on mainnet, it's also downloading the state of the contract at that point in time, which is pretty sweet. And you can import that just like you would import the implementation using the from ledger snapshot method on the environment and create your env from that. So this environment doesn't just have the implementation, it has the data in that contract at the time that you downloaded it. And again, nothing changes because you do this. You can use all the same patterns. So this is helpful when you're integration testing. If you may want to mock a contract if you're unit testing, but then you want to have more comprehensive tests where you're also testing dependencies, and you can do that with the snapshot command, which is awesome. Another point I want to make is that this is helpful when you're making changes to your contract. So let's say you change the implementation, of your contract. You can test that that it works the same, right? Like the logic may have changed, but your state or data model may have not. So you can verify that with the same snapshot, it works as intended. An area that Lee would like to explore is figuring out how we can help people that are migrating from EVM into Stellar, particularly with this, right? So if you have a contract running on an EVM, how can you test that your Soroban implementation works, with data from an EVM contract, right? I think that's pretty cool. Okay, on to the next, which is fuzzing. And fuzzing is kind of like the primary theme of this talk. It provides, I don't know how many of you are familiar with fuzzing, but fuzzing is basically a unit test or a test that auto-generates a bunch of data into your function parameters so you can test unexpected behavior. And so when we're all testing and writing our unit tests, most of our time is probably spent thinking about what kind of input you can provide to your test to like catch those corner cases, right? If you're trying to maximize coverage, you're thinking, okay, here's the data structure I pass in, it has to have this attribute so that I can hit this if statement that which will, right? Like that's kind of what you're thinking about. Fuzzing kind of takes that away and handles it for you, which is really useful. So let's, I want to differentiate fuzzing from property testing. Fuzzing, like I said, generates all that random input and tries to maximize code coverage, but first and foremost, it tries to crash your program, right? It's giving it all this garbage so that you know that you're not accounting for cases that, based on your input parameters, you say are acceptable to provide. Property testing actually does generate random input like fuzzing, but it's actually testing that certain things are true about your program after passing that random input. So it's not testing that it can break your program. It's testing, almost like an invariant, like you want something to be true no matter what is provided to your function. That's similar to what property testing is. We're not going to dig much into property testing because there are separate libraries to do that, like the prop test crate. But fuzzing is almost like a superset of property testing. You can fuzz input and then also assert invariants in your code, which we'll dig into. So I just want to call out property testing there because they're related and similar, but we'll primarily be focusing on fuzzing. Okay, so you can fuzz your code by installing the cargo fuzz command. This is not a Stellar specific command. This is the actual cargo fuzz library that you would use to fuzz any of your software that you're writing with Rust. And it's a good starting point for writing fuzz tests. When you init the fuzz command, it'll generate a fuzz directory with your fuzz tests, like a file structure to actually put your fuzz tests in, and it comes with its own cargo.lock file and cargo.toml. It's its own Rust project. And this is where your fuzz tests are going to live. When you define a fuzz test, you wrap your unit test or whatever you're implementing in this fuzz target macro, and this input parameter is the auto-generated input. So you, as the developer, define what that input is, and then you to put it in your fuzz target function definition, and the fuzz package, right, will automatically auto-generate as much input as it can that looks a million different ways to test all your code. And specifically, it's generating content with the sole purpose of maximizing coverage. So what fuzzing does is when it generates an input, it actually looks at what code's executed. And if it executed a new line that all the prior inputs didn't test, it adds that to a corpus, or basically like a file that saves all the test cases that it generated. So you can run those later, right? So you can, and it'll run forever. So if you run cargo fuzz run, it will immediately just start generating random input. Every time it tests a new piece of code, it'll add it to its corpus file. And then eventually, if you want, you could kill the process, or you could leave it running on a server somewhere so that it's infinitely generating all these test cases. Every so often, pull down the corpus file and add it to your CI/CD pipeline so that it tests a set of test cases that maximize code coverage. Okay, so let's generate our input. So in this input, or in this test case, we're going to test a transfer. We're going to transfer an amount here from A to B, and this is a little confusing. A and B in this struct are the starting balances of the associated addresses. So it's something to keep in mind. It's hard to fit code on a slide here. But this is the struct that we defined as input. So when we define this ahead of the fuzz target block, the fuzz target macro will pass input, or pass this struct with a bunch of different values for A, B, and amount to the logic implemented within the block. So this is what the block looks like. You'll notice, again, it's very similar in terms of setup to our unit test that we described earlier. We are going to be mocking all auths and then minting to address A of input.A, right? So we're initializing our starting balances. And we're not testing the mint function, which is why that we're ignoring the return result. So that is something to keep in mind. But what we are doing in our fuzz test is we're going to assert the results of the tried transfer function. So usually when you're writing tests, you're going for a specific outcome, right? If you're writing a happy path test or you're writing like an error case, you want to execute code that will raise a specific error in your implementation, and you want to validate that it actually did in fact raise that error. When you're fuzzing, you want to, it's passing all this random input, so you want to just verify that the behavior of your test is one of a given number of valid states, right, including the errors that your contract can return. So in the first two cases in this match expression, you'll notice that we're testing the expected success, right, which is that OK, that empty OK result, or we're expecting an error, and that can be one of any of the errors that we defined in our enum earlier, right? So if we get like a insufficient balance error, if we get a paused error, that's all good. That's expected behavior of the contract, right? If the fuzz test generated an address that didn't have a balance, right, and then tried to transfer from that balance, getting an insufficient balance error is what we would expect. So this is the happy path, even though it's returning an error. What we're particularly interested in is the bottom two cases, where the contract may have been successful. So you passed the given input, your contract returned, it didn't panic, but it did return something that you didn't expect, right? It didn't return something that the function signature, the contract spec, says it should transfer or said it should return. This is a unlikely outcome because Rust is strongly typed. But you can do it, and there's nuanced reasons for that. Everything that all your inputs and return types to Soroban contracts are actually bit encoded values, so you can return something that is actually not what your function declares it to be. It's kind of in the weeds, but it is possible. And the very bottom case is what we really care about here. This is when the contract failed, but it didn't fail for a reason that we thought it would. So we have that error enum that should describe all the valid cases for why our contract should fail. If it can't decode the error returned, then we got an unrecognized error, and this is a problem. This is exactly why we're fuzz testing. We want to make sure that it's not crashing or returning things that we don't expect it to return. Oh, I just skipped past all that stuff. One thing I want to note is this nested error block. Like, you may be confused with what's going on here. If it says OK in the outer layer, that means the contract actually returned something. If it says error on the outer block, then it didn't return something. The contract failed, right? It's a success versus error case. The inner result is whether or not Rust was able to decode the return value, right? So that's why we have the OK error response. It's kind of interesting to see, right? Like, you get a success response from your contract, like it actually executed and returned it properly, but it had an error decoding the result. So that is just something to note. It does look a little odd, but wanted to point that out. Okay. After fuzzing, let's talk about invariants. So we can assert things are true after abusing our implementation. So we can assert after fuzzing, a bunch of inputs for the transfer function that all balances are still greater than or equal to 0. And this is particularly valuable when you want to ensure that state is in a way or is as you would expect, right? You're generally not testing. Invariants are generally about the state of your program, not what it's returning. For example, actually, how would we test this invariant, right? Like, you could, if you have access to the internal state of your contract in your tests, right, and you're not integration testing or black box or end-to-end testing, you could inspect the state of your contract after calling it. But you could also insert your invariants in the implementations themselves, right? So when you're writing your mint function or your transfer function, you could assert within the actual implementation of those functions that your invariant is true, as we're doing here. And so this is nice, but one thing that you're assuming is that you're remembering where to assert this, right? Like if you forget to provide this assertion in your transfer function and you provide it in your mint function, what happens if your transfer function actually has a bug and it puts your balance in a non-negative state? In that case, the next time you try to mint something to that address, it'll check the invariant and it'll see that actually your balance is negative, so I'm not going to allow you to mint, right? So you want to be really careful with where you put your invariants or your assertions of those invariants if you're putting them in your implementations, because if your contract is in a bad state, then your invariants are going to block you from actually executing actions that should be valid. You can get around this by providing the debug assert macro. So you can provide a specific macro that is only that generates code that's only inputted into your implementation if you have the debug flag enabled. And then when you build for releases, this macro won't output any code. So you can get around this, but this is kind of even like beside the point that I made earlier. There's a better way to test invariants, and we can do that by fuzzing. So let's actually, instead of defining the inputs to a specific function, let's fuzz the actual functions that are called in the first place, right? So here we're defining an enum where each entry in this enum, or each member, is one of the functions on the contract. And so I define each function, and I also define the input types. And then here at the bottom, I have the beginning of my fuzz test, where I'm defining a vector of or an array of functions that I'm going to call. And this is going to test that no matter what order I call my contracts, if I call 10 mints and then a transfer, or I call a balance and then a transfer, whatever that looks like, no matter how my contract is used, the state always stays the same or stays in a valid state. So this is the implementation. The setup, again, is very similar to what we've seen before. And then you iterate over the function calls, right, the fuzzed inputs. And if it's a mint or balance or transfer, we execute the referenced code, and you'll see it kind of goes off screen here. I'll show what that looks like in a second. But we're ignoring the return types, right? Because in invariant testing, you do not care what actually is returned from these calls. You don't really care like what the inputs and return values are. You care that no matter what the contract does, the invariant is true, which is what we're asserting here at the bottom. This is the remainder of that code. It looks similar to calling another contract. The try prefix on these contract functions just ensures that you're returning a result, so it won't panic if it returns a failure. So it just helps. It's a helper function to help inspect the errors that are returned. The thing about this is that you can really push the boundary, with what you're able to test, because if you fuzz, you can generate inputs that you never would have thought of. So you can assert that the state of your contract is a given way, no matter what you can come up with. Getting the back half of our strategies is differential testing. Actually, this is the last one. Differential testing is testing that you can test two different things, and the behavior of those two things is the same. So why or when is this useful? This is useful when you're making updates to your contract. Let's say you deployed 1.0, everything's working well. You're iterating and working on 1.1. You can test against 1.0 and also verify that 1.1 behaves the same. And using the actually, sorry, before I get ahead of myself here, we have a very handy tool or feature of testing Stellar smart contracts which is that when you run your tests, it auto-generates snapshots of the ledgers of the environment that you instantiated when you're running these tests. So you'll see, in the first directory here, we have our first test's ledger state, right? So that test.1.json file has the snapshot of the ledger of the Soroban environment that you instantiated in your first test, which means that if you have a given implementation, you run your test, so it generates these snapshot files. You make a change to your implementation, and you rerun your tests. If your ledger state is different because of the change to your code, then your snapshot will be different, right? So you can just check, hey, did I mess anything up? Did I change the state of the ledger because of those changes by looking at your the diffs, right, in your IDE, which is pretty cool. So going back to my example of having a 1.0 and testing 1.1, you can download 1.0, the implementation of 1.0, using the Stellar CLI like we talked about earlier, import it, and then test that the given code blocks behave the same. The first here is the 1.1 implementation. We're implementing the token contract, assuming it's defined above this test case here. And then in the bottom, we're actually importing the downloaded contract, the WASM code that was deployed to the network that we pulled it from. And everything else is the same. So we're testing that not only did the balances remain the same, but also there was no failure prior to asserting those balances that we would expect in one, or we would expect in both, but not one or the other. Okay, we covered a lot here. We covered testing with real dependencies, testing with real data, fuzzing, invariants, differential testing. And I really want to point out that these are not mutually exclusive, right? So you can stack all of these. You can download your contracts with real data using the snapshot command. You can use those snapshots to generate environments that you generate within your fuzz tests after fuzzing your inputs or fuzzing the functions that you call in the first place. You can assert that invariants are true about the state of your program, and you can insert that all that behavior is what you would expect relative to your other versions of your smart contract. So hopefully this will give you a pretty good level of confidence that your contracts work. And I also want to point out that this isn't exhaustive. In fact, later today, Satora, I think, is giving a talk on formal verification, which we didn't touch on here. And formal verification is, goes well beyond what we talked about in this conversation. So if you're still interested in testing Stellar smart contracts after all that I talked about here, make sure to check out that talk as well. Yes, formal verification. And testing requires a lot of effort. It takes a lot of time, but it's well worth it, especially in our industry when the stakes are so high. Karen Johnson once said, who is someone that had a lot to say about software testing, that the earlier a bug is found, the cheaper it is to fix, right? If you find it before it's ever deployed, it's just a function of your time. If you deploy it, then there's the cost of making a breaking change to your users that rely on your contract spec. If you need to change your interface, there's also the cost, the monetary cost. I mean, Karen Johnson probably wasn't thinking about this, but there's a very real monetary cost or possibility of a monetary cost of a bug in your smart contract. And we just want to avoid all of that. So test your code. Yeah, test your code. And reach out to me on Discord if you have any questions about this. Thank you.